minutes now, but we're gonna manage that, I'm pretty sure. Yes, welcome to my presentation, which is, as announced, about querying environmental and road infrastructure data using a graph-based approach. And to quickly jump into the motivation, the ones who know me know already that it's always about digital twins of road infrastructure, and that it's also always about providing a reliable information base for decision support. And in this case, it's particularly about enabling some correlation and forecasting in terms of deterioration processes in road infrastructure. And if we go a bit more precisely into the research gap, if we look into deterioration, then it's a question, what do we have? And what we have is some research on deterioration processes. So we know from some models that are already developed that there's some dependency on deterioration processes and road infrastructure on internal factors such as material properties, structural properties, but also assets influencing each other, and then some external factors like climate, for example, heavy rainfall events, temperatures, things like that. But all the models that are developed and all the studies that are conducted always use a unified database, which is in fact not the case. If we look into real-world road infrastructure systems and how they are managed, we have to deal with a lot of heterogeneous distributed data sources. We see here the example of Germany that we also used for our case study. We have some road data that you can fetch through some web services. We have an asset management system, which is even worse. It only supports file-based data exchange. And then we have some climate data that we can fetch from the Climate Data Center, which provides a nice record of climate data from the last decades. So what we want to do is kind of close this gap between the heterogeneous data sources that we have on the one side and the unified database that we need to do some deterioration investigations. And we do this with a digital representation of road infrastructure that captures and enables the evaluation of internal relationships between the data, so between assets, for example, spatial relationships, and also external relationships, so for example, like which bridge was affected by which climate that was recorded. And we don't want to do this just for one asset, because then we could just load everything into a GIS system and associate it manually. We would like to do this at scale for all 50,000 bridges, for example, that are in a road infrastructure system. So our approach has to be scalable. And of course, we are dealing with heterogeneity in our schemas and also some data distribution between different subsystems. So what is our take on that? What we propose is a graph-based system of systems, digital representation of road infrastructure, and it's basically divided into two layers. I guess it's not really readable, but the layer one is basically the graph representation or the representation of different subsystems. And as we are interested in linking heterogeneous data sources, we apply here mainly knowledge graph representations that facilitate the linking of heterogeneous data. And then, as those subsystems are still not connected, we have the second layer where we then connect them through an orchestrated querying, where we then, at the end, enable the cross-system querying. To look a bit further into detail what's within these layers, I mean, we have here on the left side the Climate Data Center. This is a database we don't touch, we just integrate it. Here we have some climate data that is stored in a relational database. And I mean, it's basically time series data, so having this in a relational database is totally fine, and we should keep it like that. Then on the other side, we have our other legacy data sources like the road data, for example, or the bridge data. In this case, we might be interested in some relations that exist in the data, so we create some graph representations of the data and have some, graph database instances with some graphs there representing these data sources. And then, of course, we're interested in the relationships. In this paper, mostly spatial relationships. So we have the internal relationships, spatial relationships between the assets. And then, of course, we also want to integrate the weather data or the climate data that we have. So we also have the relationships to external data sources or to external entities. And then, at the end, we still want to evaluate these relationships cross-system-wise. And this we do by creating something like an overlap between the systems. So if we have an entity, we represent this entity in several graphs that at the end allows us to assign data sources to each other. Giving an example, a bridge, for example, is represented as well in the bridge graph, where some bridge condition data is stored, but also in the internal relationship graph, where its relation to a road asset is captured. And then in the interface relationship, we have graph, we have a relation to a weather station, for example. Modeling these relationships in a scalable manner is a thing, and this is one of the core parts of this paper. And here the challenge arises from the fact that we can't model spatial relations for entire road infrastructure systems explicitly. Because if we do that, we would end up in a very dense graph. What is the reason that we use a reference-based approach? So what we basically do is we implement linear referencing in our graph structure. We use the road network as reference elements. Doing this for assets, we explore this in previous work. So I don't want to go into detail here and save a bit of time. But the core idea is basically that we represent assets as intervals along network edges of the road network. And what we're doing for integrating the environmental data or the climate data is basically similarly. So basically we map the areas that we have around some weather stations, or we map the areas onto these reference elements, also locate them via a start and an endpoint, and also encode this in our graph structure that we can see here on the right, where we have basically a representation for the reference element as node in the graph. Then we have the environmental area as a node in the graph, and then through the relationships encode the positioning of the area on this linear reference element. And at the end, we want to evaluate everything cross-system-wise, so we need something to connect. And as both the environmental areas and the assets are referenced to the same road network element, we can use the representations of the road network that now occur in both graphs as a connection point. So giving an example, if you're interested in if a road section, for example, was influenced by a certain weather or lies in a certain environmental area, we just have to query for the overlapping the overlapping situation between the representing intervals in the graph. Speaking of evaluation, here we are. We're using knowledge graph representations for relationship modeling. So at the end, every relationship that we have in the graph corresponds to a certain subgraph structure. In the other direction, if we would like to associate elements based on its relations, we are basically performing a pattern matching where we look which instances possess a certain relation encoded through a certain graph structure. So relation is represented by a pattern graph, but the point is still we have our subsystem distribution that we like because it enables us to don't overcomplicate different schemas. But if you look at a very simple example where we have, for example, a bridge condition, and we would like to associate this with heavy rainfall events occurred in a certain period of time, then our pattern graph will span several subsystems. So we need a strategy that allows us to do that, because we can't just simply send a single cipher query to a database endpoint and the problem is solved. So what we do here, we use our subsystem overlappings and basically cut our pattern graph and decompose it into several sub-pattern graphs, always using the subsystem interfaces that we have. And at the end, it comes down that we have something like a query plan that we can execute in Python, or where we wrote a simple script to execute that in Python that basically sends the single subqueries to the database endpoints, fetch the results, and uses this for creating the subsequent query. And with this, it iterates through the different systems. It doesn't matter if it's a relational database system involved or if it's just graph databases. At the end, we have a nice collection of associated data sets that we can hopefully use. To go a bit more in detail for the last remaining minutes that I have, we can describe our query plan as a dependency graph where we basically represent every system as a node, and the overlaps as something like a relationship. And then this dependency graph basically tells us how we have to iterate through our system. And for a simple use case, it would look like this: that we, for example, query our internal relationship graph for location of a bridge within a road network. Then we can jump to the interface relationship graph. There we can look which weather station is responsible for this bridge. So which weather station measures weather that happened on the bridge. And then we can do a fan out basically in our interface graph where we once query the climate data center for the corresponding climate data, and on the other side the bridge condition data. And now we have to hurry up, I guess. So we jump quickly to results and conclusion. We account for heterogeneity and data distribution through our system of system architecture. We have independent subsystems. We encode spatial relationships in a super nice way. And we enable cross-system evaluation through orchestrated querying. Limitations are issues in legacy data remain. So applying directly correlation analysis and forecasting, we still suffer from poor quality of legacy data. That's not solved yet. We have high temporal heterogeneity in our data that we neglect so far. But if it comes to some future ideas, I mean, right now we define our define our query plan per use case. But technically, we could also just describe our subsystem structure in a dependency graph and then generate our query plan dynamically, which would be much nicer and also a bit an agentic system. And thanks for your attention, and I'm open for questions and hope it was